So, hello, welcome to the last lecture on time-dependent perturbation theory. So today we'll be going to discuss two topics. One is dipole approximation, and the other one is a selection rule in dipole approximation. So in the last lecture, we have seen that the transition rate for the atom field interaction in quantum theory, and we have got two expressions. One is the transition rate for emission, and as well as we have also got the transition rate for absorption. So these were the those expressions, and we have seen that there are in case of emission transition rate, there are two delta function. One is this chronicle delta. So here the emission is possible only if the final photon number must be equal to the initial photon number plus one, and the final energy must be equal to h cross omega times less than the initial energy. So that is the condition for the transition rate for emission, and similarly we have got the expression for transition rate for absorption. Okay, now what we are going to discuss is what is the importance of this particular inner product. So there is an inner product here, psi f atom e raised to I k dot r e dot p psi a atom mod square. Okay, so we are going to simplify this expression, because in order to get the non-zero transition, then this term should also be non-zero. Okay, so before going to the condition for non-zero value of this inner product, first we can make an approximation. Otherwise, it will be difficult to calculate this particular inner product. Okay, so we are going to start with the inner product psi f atom e raised to minus I k dot r. Okay, it can be in case of emission it is minus, and in case of absorption it is plus, raised to minus I k dot r, and e dot p psi I atom. Okay, now how to calculate this inner product? Now the first thing is if you recall your k, the magnitude of vector k is 2 pi by lambda, where lambda is the wavelength of the light of interaction, the interacting electromagnetic wave. And what is r? So r is basically is corresponding to the size of the atom. Okay, so what is the size of the atom? So if you look at the atom, the atomic size will be approximately in the order of 10 raised to minus 10 meter, okay, in the range of angstrom. And what about wavelength? Okay, so usually the wavelength would be in the order of nanometer or a micrometer, because we'll be using a visible light or ultraviolet light. So the lambda will be in the order of 10 raised to minus 6 meter. Okay, so if this is the case, then what would be the average value of k dot r? So if you look at k dot r, or the magnitude of k dot r, what would be this approximate value? And k dot r will come is 2 pi by lambda times a0, or a0 we can call it as a Bohr radius, and it will be approximately 10 raised to minus 3. So that means your this k dot r value would be very small in case of an atom field interaction, if your incident or if your interacting electromagnetic wave is in the visible region or UV region, visible or UV region. So okay, so that if that is the case, if k dot r comes in the order of 10 raised to minus 3, then what would be the value of e raised to plus or minus I k dot r? Okay, so you can recall any exponential function e raised to plus or minus I k dot r can be expanded as 1 plus I k dot r by 1 factorial plus I k dot r square by 2 factorial plus so on. So the first term is 1, or the second term is in the order of 10 raised to minus 3. And 10 raised to minus 3 is very small compared to 1. So therefore I can assume that e raised to I k dot r, or I can make an approximation that the e raised to I k dot r is approximately 1. So this approximation is called dipole approximation. Okay, so remember this dipole approximation is not valid if the wavelength is very small. Okay, when you're going to gamma ray and all, then you cannot use this approximation. So if the lambda is large, and if lambda large and small size for smaller atoms, then I can easily use the dipole approximation. Okay, so remember this is an approximation, so it is valid with certain restrictions. Okay, now if that is the case, then how will be your inner product? So then your inner product psi f atom e raised to, okay, maybe I can write plus or minus I k dot r, then e dot p, I think. Yes, e dot p psi I atom can be approximated as psi f atom e raised to plus or minus I k dot r can be approximated as 1 and become e dot p becomes psi I atom. Okay, so if you want, we can take this e outside, so it become e dot psi f atom p psi I atom. Okay, now our task is to calculate this particular inner product. Okay, now it is possible to express this inner product in another way. So for that we have to use some one result. So the result is, so consider the commutation between the x and px. So what would be the commutation between x and px? So it is very well known to us. It is simply ah cross, because x and px are canonically conjugate operators, and the commutation between any two canonically conjugate operators is simply the I times h cross. Okay, now what would be the inner product between, sorry, what would be the commutator between the x and the Hamiltonian of atom? The Hamiltonian of atom will contain two things. One is the momentum, okay, p square by 2m plus v of r. Okay, now the x with v will commute, so that commutation would be 0. So this would be equal to x with p square by 2m. Now p square can be expanded as px square plus py square plus pz square. P square is px square plus py square plus pz square. Okay, now x will commute with py, x will commute with pz, so those two commutation would be 0, and therefore the remaining thing would be, you can take your 1 by 2m outside of this commutator, then x comma px square. Okay, so that become this you can do, okay, very well, because this result is very easy to calculate. Okay, so I'm skipping the steps. So if you want, you can do it. Now the x with px square would give the result to I h cross px. Okay, so these two would cancel, and what you get is equal to I h cross by m times px. Okay, so what is the takeaway of this? It is the momentum operator px can be written as m divided by IH cross, the commutator between x and the Hamiltonian of atom. Okay, so we can take this to next page. And how can we write the total momentum? And total momentum operator, if you use this analogy, so the total momentum is simply px plus py plus pz. So this become m by h cross the position vector r, then the Hamiltonian of the atom. So I can rewrite my momentum in terms of the position vector and the Hamiltonian in this form. Okay. So this result I am going to use in our the previous inner product. Okay. So the previous inner product is the original inner product, and after the dipole approximation we can write that in this way. So therefore, the psi f atom e raised to plus or minus I k dot r e dot p psi a atom is approximately, that's after dipole approximation. We can write that is E dot psi f atom momentum operator psi I atom. So this momentum operator I can write, so m by IH cross can be taken outside, E psi f atom, the commutator, position vector, and the Hamiltonian of atom times psi I atom. Okay, now I can expand this commutator. So this become again m by IH cross the unit vector f atom, then operator r atom minus H atom times operator R psi I atom. So we can divide this inner product into two. Psi F atom R atom psi atom minus psi F atom R psi atom. Okay, so when this the Hamiltonian acting on psi I atom, so remember the psi I atom is the energy eigenstate of the atom. So therefore we'll get it becomes EI psi I atom. And again this Hamiltonian is a Hermitian operator, so it can act on the prefactor as well, okay, in the bra vector as well. So therefore this H atom acting on psi f atom would give EF psi f atom. So I will take this line to next page. Okay, so this can be as m by IH cross unit vector psi f atom position vector become EI times psi I atom minus psi f atom EF R psi atom. Okay, so this can be simplified very easily. So here EI is just a number, can be taken outside. EF is also just a number, just real numbers, because these are the eigenvalues corresponding to the Hamiltonian, which is the Hermitian operator. So obviously the CI and EF are just a scalar number, it can be taken outside, and therefore this become EI minus EF so EI minus EF in the bracket psi f atom R psi I atom. Okay, So this is the result. Now we can bring our the original formula. So these were the formula for the gamma emission, the transition rate for emission. So for transition rate for emission, this inner product I can write in this particular fashion. Now we can remember that this EF minus EI must be equal to H cross omega, or EI minus EF become minus H cross omega. Now when you're taking this mod square, and then it will become minus H cross omega square, so that obviously become plus H cross square omega square. Okay, so therefore the result would be 4 pi square E square by M square omega times V n plus 1, the drag delta NF comma Ni plus 1, drag delta EF minus EI plus H cross omega. Then there will be M square by H cross square H cross omega square. Then there would be mod square E times psi f atom, sorry, E dot R psi a atom mod square. So there we got a very detailed expression for the transition rate for emission using the dipole approximation. So here we have assumed, we have already applied dipole approximation, and similarly if you want we can write the expression for the transition rate for absorption as well. Okay, now so the main the takeaway is this: if you are using a dipole approximation, if you're using dipole approximation, then your inner product psi f e raised to I k dot r e dot p psi I is psi f atom, psi I atom can be written as I m omega. So this can be written as omega fi e dot psi f atom r psi I atom. Okay, how I have written this? So this nothing but the same expression. If you take I to the upper side, it become minus I, and this become EF minus EI, and EF minus EI I can write H cross omega, or more correctly I can write H cross omega Fi. Okay, so nothing great here. So the same expression I have written here. Okay, so this is basically what is called the dipole approximation, and we can find out the transition rate of the atom field interaction. Now the last thing is the selection rules, because since this is the inner product which is comes over here, then there are certain restriction for the transition of atom. Okay, so not all transition is possible in case of atom field interaction. Okay, so that we can discuss by discussing the selection rules, or electric dipole selection rules. Okay, so the main thing is in order to transition of atoms, the first thing is psi f atom or psi I atom must be non-zero. Okay, so whenever it is non-zero, then such kind of transition is possible, and the entire transition rate we can find out from the previous expression. Okay, now, and there is one more thing. There is a the polarization term here, this E. So E dot this one. So this term must be non-zero. Now there are simple way to explain this problem, because if you look at this, yeah, if you discuss the parity, the R has parity -1. Okay, so the R has the odd parity. Now the psi f atom and psi a atom will have its own parity. Okay, suppose the angular momentum quantum number is Li for the initial state, and angular momentum quantum number is Lf for the final state. Okay, so since R is already having an odd parity, then the Lf and Li cannot have the same parity, because if Lf and Li has the same parity, suppose if Lf is odd and Li is also odd, then the product will become even. Then therefore the total parity will become odd. Okay, so if all, okay, anyhow R is already an odd parity. So therefore, in order to get non-zero, the parity of the initial state and final state must differ. Okay, so since R has odd parity, then because this inner product will be 0 if the parity is odd. Okay, since R has odd parity, then in order to get the total parity even, the psi I, or the initial state and final state must have different parity. So this is the very qualitative way of explaining the selection rule. So that means if the psi I has odd parity, then the psi f must have even parity for non-zero transition, and vice versa. If psi I has even parity, then psi I must have an odd parity again for non-zero transition. So that means if the atom, initial state of the atom is 1s, then the final state cannot be 2s. So 1s to 2s transition is not possible, because 1s has L equal to 0 and here also L equal to 0. So that means it has same parity, so it is not permissible. Okay, but from 1s to 2p, that is permissible. Okay, so the parity, there must be difference in parity when the atom is going from one state to the other state. Okay, or in other words, I can write that Lf minus Li must be an odd number. Okay, so this is only one condition. There are other conditions as well in case of the azimuthal quantum number also. Okay, so in order to get the detailed selection rules, so what we have to do is we have to express the position vector in terms of spherical harmonics. Okay, so that is the detailed steps are given in your textbook. So I will just mention it how to write in spherical harmonics. Okay, so what we can do is your E dot R, it is possible to write E dot R in the form of square root of 4 pi by 3 times R, then minus I. Okay, it's a unit vector, so minus I. Okay, so since we are using I for, so minus x plus I y cap divided by root 2, the spherical harmonics 1 1 plus x plus I y cap divided by root 2 y 1 minus 1 plus z cap y 1 0. Okay, now your psi f atom E dot R psi atom. Now the atom, it is possible to write atom as R NL YLM theta phi. Okay, so the state of an atom you can write as R NL of R YLM theta phi. So we can use the same index. So NF R NF LF Y LF MF theta phi E dot R R NI LI Y LI MI again theta phi. Okay, now in this way we can rewrite the inner product. Okay, so if you do it carefully, then we'll get a very long expression. So which contains the Krebs coordinate coefficient as well. So if you do it, okay, so there are some steps here so that we can do as a homework. And finally, what you'll get is you'll get this kind of expression: Li, comma M, Mi, comma M prime, then Lf, Mf. Because we can write R in terms of y11, y1 minus 1, y10. Okay, so this first element it is 1 already, L is 1. So that one which comes over here, sorry, it's Li1, Li1, Mi, M prime, LFMF. Okay, so this one which comes from here because all the first element is 1, and M prime, the M prime stands for the second term. The second term can be 1, minus 1 or 0. So this means M prime can be 1, 0 or minus 1, and LIMI, LFMF. So LIMI are the initial angular momentum quantum number and azimuthal quantum number, and LFMF the final angular momentum and azimuthal quantum numbers. Okay, so in order to get non-zero, okay, so this become non-zero only. So there are some conditions for it. What are those conditions? The first one is your MF must be equal to Mi plus M prime. So where M prime is 1, 0, minus 1. That's one condition. Now the second condition is your LF. LF must be between Li minus 1 and Li plus 1. Okay. So LF is concerned. So these are the two selection rules. Okay, so from this we'll get we can summarize the selection rules as your FMF minus Mi equal to M prime. So that means it can be 1, 0 or minus 1, and LF minus Li. Okay, so it becomes from Li plus 1 to Li minus 1, and you can show that this LF minus Li must be equal to odd integer. Okay, so this we have already discussed qualitatively earlier, so just a minute ago, but we cannot able to discuss this fact because in order to discuss this fact, we should have the idea about the spherical harmonics. Okay, so this is our conclusion. So this is the final selection rules of electronic transition. That is the electron going from one state to the other state with the interaction with atom. So it's a selection rule with dipole approximations. Okay, so with this, I think we have completed the entire topic of time-dependent perturbation theory. So we have started with in very simple way That is, we have introduced what is time dependent perturbation theory. We have given a general formalism for it, and we have seen that there is finding the transition rate is the important point in case of time dependent perturbation theory, and we have applied the general formalism in case of the atom field interaction. So we have seen that there are certain difference when you're going from the classical the atom field interaction theory and quantum atom field interaction theory, and finally we could able to achieve certain conditions known as selection rules for the electronic transition of atoms whenever it interacts with the field. Okay, so with this we are winding up the discussion on time dependent perturbation theory, and hopefully we'll start the next topic, which is the scattering, the quantum scattering, maybe in the next class. And before that, we may discuss certain problems, or and we can have some doubt clearing sessions in next class. Okay, so we can stop it here. So see you.